Welcome to your AP Statistics lesson on understanding randomness. I'm here today with my sidekicks, Scout and Daisy, and the three of us are ready to teach you all about understanding randomness and using it to create simulations. All right. So, what is it about chance outcomes being random that makes random selection seem fair? People feel like, oh, okay, it was selected randomly. That's fair. No one can guess the outcome before it happens. And also, many times that we're doing that, we want equally likely outcomes. And so, when we draw names from a hat or select a random digit, all the results are equally likely. Um, now, that's not to say all events are equally likely. Many times, as we're going to see later, the individual components are equally likely, but we're looking at the components in some sort of combination. And once we start combining components, we no longer have equally likely outcomes. So, for example, if you've got a coin near you, pick heads or tails. Flip the coin. Does the outcome match your choice? Did you know before flipping the coin whether or not it would be matched? Um, Statisticians think of randomness as a tool and not just a haphazard um, tendency of events to occur. Um, for events to be truly random, there has to be a pattern and the results, but you can't know what the next result is going to be. So you would think, okay, that's easy to, create random digits or other random values, but it's not. It's actually really hard. Computers are a great way to produce what are called pseudo-random numbers. They behave like random numbers, but because they are generated by some sort of program, they aren't truly random. But for our purposes, they're going to be good enough. There are ways to generate random numbers so they are both equally likely and truly random. Um, but again, we'll probably rely on the programmed options whenever we can. The best ways we know to generate data that give a fair and accurate picture of the world rely on randomness. And the ways in which we draw conclusions from those data depend on the randomness too. When we are doing random selection, that allows us to have faith in that we have a good chance of having a representative sample. Okay, so later in this chapter, or this unit, we're gonna learn how to create data through sampling and surveys, and then we're also gonna look at how to create data through experiments. There's a third way to create data, which is called simulation. Sometimes it's just going to be too expensive or unethical or otherwise impossible to actually run a particular event over and over. And so we simulate the event and run those many times. Okay, so within a simulation, there's some important words for you to know. The sequence of events we want to investigate is called a trial. Okay, usually, the question is that we're interested in is some sort of result from that trial. The basic building block of a simulation is called a component. Okay, so several components make up a trial. After we finish with one trial, we record our response, the value of our response variable, and then we repeat this process. In theory, we repeat it many, many times. For our purposes, just to get familiar with it, we'll just be running it a few times. Computers are awesome because you can program the simulation into them, rely on that pseudo randomness, and you can run thousands of trials fairly easily. All right. So, with simulation, you want to first identify the component to be repeated. That is the little baby building block that's going to build trials. And then you want to explain how you will model the component's outcome. Then explain how you would combine the components to model a trial. So remember, a trial or run is a sequence of events we are pretending takes place. We want to state clearly what the response variable is. We have to be very clear of what information we're trying to get from each trial. Then we're going to run several trials. Like I said, if we were programming computers to do these, we would have them run thousands of trials. But since we're doing this by hand, we might use a random integer generator, but we're not programming the whole process. We will run 10 unless it's specified otherwise. You want to give an example. You want to have one run or one trial. You want to show exactly what those results were and how you interpreted them. You're going to collect and analyze and summarize the results of all the trials in a table or graph of the response variable. And then you're going to state your conclusion in the context of the problem. So let's look at one example. Suppose a cereal company places one of 4 toys in every box of cereal. Furthermore, the company claims that each toy is produced in the same quantity, so each of the toys is equally likely to show up in a randomly chosen box. Suppose I want to get all 4 toys, but it takes me 15 boxes to find each of the 4. Is this evidence that the toys are not uniformly distributed? Estimate the probability that it takes 15 or more boxes to get all 4 toys, assuming that the company is telling the truth. Okay, so we're going to assume that we have equally likely events, that whenever we open a box of cereal, we pull out any one of the 4 toys. All right, so our component to be repeated is opening a box of cereal and identifying the toy. That is what in real life we are trying to simulate. So now we give the model for how we're going to do that in a simulation. Since each of the 4 toys is equally likely, we will use random integer 1 to 4 to simulate an outcome. Okay, and so one toy will be labeled 1, and the next one 2, the next one 3, the next one 4. Okay, so for a trial, the trial is going to be made up of a bunch of our simulated components. So we will continue to generate individual random integers until each digit, 1 through 4 inclusive, is generated, keeping track of the number of integers generated. Okay, so you're going to write them down. Okay, once you get all of them represented, then you're going to go back and count how many components it took, how many times you had to generate an integer. The response variable is that count of the total number of integers generated in order to produce each digit 1 through 4 at least once. So for example, if I had 1, 3, 1, 2, 2, 1, 3, 4, I would stop finally on that 4 because that was the last digit that needed to be represented. And there are, let's just double check this, 1, 2, 3, 4, 5, 6, 7, 8. All right, it would have a result of 8 because it took 8 simulated boxes of cereal for me to get all 4 toys. So I did this several times, and you can see my results here in a dot plot. And not a single one of them is equal to 15 or more. They don't even come close to it. 8 is the maximum number that I got. Now, these are the probabilities we're getting from this is from simulation and from something data we're creating. It's not based on theory. Okay. So based on my results, we want to always start with that little phrase. Based on my results, the probability that it takes at least 15 boxes to get all 4 toys is approximately 0. It appears that the company could be lying, but we should conduct more trials before making such accusations. Right? So, if you think about it from a marketing standpoint, they're probably going to pick like the toy that's everybody's favorite toy. Okay, or just any one of them and make it more scarce than the others, so that you have to buy more boxes of cereal to get all 4. Because you know how it is. Once you've got your mindset on, oh, I want all 4 of these, and you've got 3 of them, you're like, "I'm gonna buy this cereal and eat it every day until I get that final, toy." So my collection is complete. All right, guys, that's it for this video. So do the problem to try on your own, and I will see you in class unless you need to come see me ahead of time, or if there's something small I can help you with, feel free to email me. I hope you have a great day, and I look forward to discussing this further with you.